Hello everyone. In today's session, we are going to dive deep into one of the most powerful tools in data science and machine learning. So, principal component analysis called as PCA. But before we jump into PCA itself, let's answer some fundamental questions or foundational questions, you can call it. So, like, what is dimensionality? And why do we need dimensionality reduction? The next question is, what role do linear algebra concepts like matrix, dot products, transpose play in all this? That we should understand priorly before we dive into the concepts of PCA. Well, answering the questions one by one. What is a matrix and how data is represented? For that, I want you to imagine that we are dealing with a data set from a hospital where each patient's record includes their height, weight, ECG reading, cholesterol level and other medical information for all the patients. We can represent this data set as a matrix. Maybe you can think of it as a table also. So each row is a patient information and each column is a feature. That is, we called it as height, weight, ECG, cholesterol levels, etc. Right? Heart rate, blood pressure, etc. Whatever. So, if we have 100 patients, that is row, and 50 features, that is the height, weight, ECG, cholesterol, all this information, a matrix has a dimension of 100 into 50. So basically row into columns. Well, now the second question is, what is dimensionality reduction? Now here's the deal. Not all the 50 features are equally important in the medical information which we have taken. Not all the features contribute equally to the output required. Some may be highly relevant to the predicting heart diseases, while others are just noise, less relevant. For example, for a heart failure, if you think the heart rate and blood pressures are of high relevancy, whereas the name is not of relevant, it's of less importance. So dimensionality reduction helps us to answer which features matters the most and can I reduce the number of features without losing too much information. That is exactly what PCA helps us to do, reduce the number of features or dimension while preserving the essential structure of the data. Now, I want you to understand what is the transpose of a matrix. I'll tell you when this is really important. But let's say if A is a matrix of shape m into n, that means m rows and n columns, the transpose of A, where it is represented as A superscript T, flips its rows into column and vice versa. In our above example, it is 100. If it's A is 100 into 50, then A transpose is 50 into 100. Now, I told you why this transpose is required. That's because we are basically doing a dot product of the matrix, which we use to find the similarity between each element. Now let's talk about dot product. Suppose if you want to multiply A into A transpose, which is the dot product, it's going to give us the matrix shape of 100 into 100. It compares each patient with every other patient. Again, A transpose T into A gives us 50 into 50. This compares features with features. Okay, so depending on how you multiply, you can explore the similarity between features and similarity between the data points. So when you compare similarity between features, it's going to be A transpose multiplied with A. When you find the similarity between the data points, which is the row, you get A into A transpose. So these are dot products. So that's why I introduced priorly the transpose. Okay. So which involves the matrix and its transpose. Okay. This is important when choosing how to decompose data. Okay. Okay. Now decompose meaning like when you defragment the data in the matrix. Okay. Now another important term is you should be aware of what is orthogonal. Like orthogonal means like two vectors are at right angles. They have a zero correlations. So the angle between them is 0 means cos 90 degrees is resulting to 0, right? 0 degrees. So if the matrix you create as orthogonal vectors, it leads to something special, the identity matrix. Suppose if you multiply A into A transpose or vice versa, which is A transpose into A, if it leads to identity matrix where diagonals are 1 and off diagonal elements are 0, means the vectors are orthogonal, which means the direction between each element is perpendicular, or in other words, they have 0 correlations. So if it is 1, then they have more correlations. If it is -1, they have negative correlations, positive correlations or negative correlations, in other words you can say. That's the key to PCA. We want to find the direction of the data set that are perpendicular and ordered by how much variance they carry. So basically we need to find the direction of the data points and then ordered by how much spread they carry. So covariance matrix. Before we get into PCA, we need to come across another term which is covariance matrix, which computes something called as it measures how much one features vary with another. Okay. So if features varies a lot with another, they are strongly correlated. If it doesn't, then they are more independent. They are not correlated. They do not have a dependency on the other. Both are independent. So covariance matrix is like you can see the formula on the screen. It's A transpose into A dividing by n minus 1. Okay. Now I want you, as earlier you could have come across something called as decomposing the matrix, right? So basically I told you it is to like segment or divide the matrix. Okay. So this matrix decomposition now comes with a magic. It means like breaking a matrix down into smaller or meaningful parts. That's a beautiful intuition here. That is really very much like an interesting part which involves this decomposition is very like interesting, because it gives you a rotation. When you decompose, what happens is you basically divide the matrix into 3 matrices, wherein the first matrix talks about the rotation, the second matrix talks about the stretching, how much in that direction. So you're rotating in one direction, which is which is actually a vegan vector. We will be discussing later. And then how much to be stretched in the direction, and then again you're rotating it back. So that is basically the flow of matrix decomposition. Well, let's say you have your data is scattered in a dimensional space, okay, which you can not visualize directly, because there is, see, if it is a 2D or 3D, you can visualize it as x-axis, y-axis, or x-axis, y-axis and z-axis relatively, right? But when it goes to n-dimensionality, so viewing these data points in a hyperplane is highly complicated, and it is very computationally expensive also. So you rotate the coordinate system to align the direction of the maximum spread. So see, yeah, I want you to refer the previous statements of matrix decomposition, which basically involves rotation, stretching, and rotation back. Okay, so why we are rotating is you rotate the coordinates such that to align with the direction of the maximum spread. See, you are not rotating it randomly, but you have to rotate in the angle in such a way that the data points are at maximum spread. This is PCA step number 1. Okay, now slowly we have to know what are eigenvectors and eigenvalues. Now again I want you to refer to the beautiful intuition which we described, right? What is that? That's rotation, stretching, and rotation back. So I want you to relate this rotation on the first step what we do to the eigenvectors. So in what direction you should rotate? That's basically the eigenvector, which talks about in which direction you should rotate the n-dimensional data points. Because not in all angles the data spread is longer. In certain direction the data spread is longer, and we need to figure out that direction. That is going to be a PCA. So in which direction you should rotate, that is exactly the eigenvector. See, and to tell it again, eigenvectors tells us the direction to rotate, whereas eigenvalues tells us how much is in that direction, how long is in that direction. It is telling you, okay, it is measuring you the length of the spread, or technically you can call it as a variance. Okay, now we compute this from the, how do you compute this? Okay, we need eigenvectors and eigenvalues for like rotation, stretching, and rotation back. But how do we calculate the eigenvectors and eigenvalue? Is from the covariance after calculating the covariance matrix. Okay, so the direction with the highest eigenvalue will be your principal component analysis, that was PCA 1. It captures the most variance. So the second principal component, which is called as a PCA 2, captures the second most longest spread. Okay, fine. Now, so that's basically we are doing. We are actually rotating the coordinate system to align with the PCA 1. That is the longest maximum spread we want to find. In that direction, we are orienting the high dimensional space. Now, once you have done the PCA, we have not yet done with the project, dimensionality reduction, right? So we come to do this dimensionality reduction, we come across a beautiful term in mathematics called as a projection. So once you have PCA 1 and PCA 2, we can project a high dimensional data onto a new axis, say PCA 1. This means you are not throwing away any data. You are actually compressing the most important variation in a single line. So that's actually dimensionality reduction. After you have projected the data, the dimensionality reduction has been performed. So have a quick summarization of these steps again. So representing, what you are doing is you are representing a data set as a matrix, rows and columns, where row represents the sample and column represents the features. Okay. Second, you are creating the data. How do you do that? You are subtracting the mean from each feature. Third step is what you are doing is you are computing the covariance matrix using the formula which I have earlier mentioned. Okay. Now you are doing a eigen decomposition or SVD. Okay. So what is eigen decomposition or SVD? Rotation, stretching, and again rotating back or performing the transpose of the vector. Now in the fifth step, what we do is we select the top k components based on the eigenvalues. So basically we are picking the top k eigenvalues. So finally in the sixth step, what you are doing is projecting the original data onto these new components. So PCA 1 and PCA 2, and we are discarding all the other dimensions. Okay. So PCA, I just want to conclude saying that PCA is not just about reducing dimensions, it's about uncovering the most meaningful informations in your data. I want you to comprehend this. It combines beautiful math, linear algebra with powerful insight. Okay, I hope this video has given you a powerful insight, and this is Lakshmi from the Skyverse, unraveling the infinite possibilities of data. Thank you.